Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and I think we have a really great hangout planned for you, although I say that every week because we always have great hangouts planned. I think you're going to enjoy this one, though. Astronomers using the Hubble Space Telescope have pointed it at WASP 43b, an exoplanet that we'll be talking about later on, and made a thermal map of it. We'll also talk about what that is. So before I get started with this, I want to mention real quickly that if you're going to be in New York, I want to remind you that they have the Hubble at 25 exhibit going on there. And I also want to note that they have a next Wednesday, they're going to be having a public event where they'll have astronauts who's worked on the Hubble Space Telescope giving some remarks. So if you're in New York, I would highly encourage you go and check that out. It sounds like a lot of fun. So with that, I'll go ahead and get started. The thermal map of WASP 43b. That's the topic of today, and joining me to help with the discussion is Dr. Carol Christian, as she is always with me every week. She's the outreach scientist for the Hubble Space Telescope. Hi, Carol. Also,
hello.
Also with me is Scott Lewis, who is the driver of the internet for us. He monitors all the social media streams and posts images and comments and keeps things going while we're online having the discussion. Hi, Scott. Welcome.
Thank you, Tony. How's it going?
Oh, really good. So why don't you do this week? Tell people how they can interact with us on social media.
A multitude of ways that you can interact with us. Since we're streaming live on YouTube, you can make comments directly onto YouTube, but we also have the Q&A app enabled. So on the bottom left-hand side of the window, you should see a little yellow prompt. It'll actually open up a window and allow you to ask us questions directly. We can select them. That's available on YouTube and at Google+. And we're also over on Twitter using the hashtag Hubble Hangout. And I will be tweeting throughout this entire time, so I would love to tweet back at you. And also the event page, where I will be posting some images as well. So many ways for you to be in touch with us, and we love getting your questions and comments and answering them on air.
Okay, that's with all things when you're talking, Scott. I phased out there. Did you say the Hubble Hangout hashtag part two?
No, I don't ever. Yeah.
Yeah. Okay. Okay. Good. I was reading while you were talking. All right. So today we have with us Dr. Kevin Stevenson. He's a NASA Sagan Fellow at the University of Chicago, and we also have Laura Kreidberg. She's a grad student also at the University of Chicago, here to tell us about their research where they looked at an exoplanet. And why don't, Kevin, I'll start with you. Why don't you give us a brief overview of the work you've done, a brief summary of the work you've done, and then I want to go into exoplanets in general just a little bit.
A lot of the work that I've done focuses on extrasolar planets, particularly the characterization. So what I try to do is try to understand what the atmospheres of these exoplanets are made out of. We know typically they're fairly large, gas balls, and they can have hydrogen and helium, but we're more in the other aspects, water, carbon monoxide, carbon dioxide, methane, that sort of thing. And to understand really the circulation, the temperature, everything about these planets that can tell us a little bit more about our own solar system and the galaxy as a whole. So I really try to understand exoplanets and where they come from based off of our measurements with, for example, Hubble Space Telescope.
Oh, great. So let's talk about that a little bit. So what are you finding out about the characteristics of exoplanets? I mean, this is a brand new field of study, relatively speaking. Exoplanets are just everywhere now, it seems. So what are you finding out about them?
Well, there's certainly tons of surprises everywhere we look. We've made measurements over the last 10 years, and it seems that every time we make a prediction, something comes up and we see something completely differently. It's not that the predictions aren't accurate, it's just that the universe is so much more diverse than we expect. So sometimes we might hope to detect methane and we don't, and sometimes we might expect to we don't expect to see it and we do. For example, with the observations that we're doing here, we would expect maybe that the planet might be similar in temperature on the day and the night side, and this was in fact surprising when we saw that the day side was so much hotter than the night side. So it just goes to tell you that there really is a diversity of exoplanets out there, and we're just scratching the surface.
Yeah, and to add to that, I would say that when Kevin talks about this diversity, it's really, we've uncovered planets that are completely unlike anything that we have in our own solar system. And so the planet that we studied that we're going to be talking about today is incredibly hot. It's orbital period is less than 24 hours. And to give you a sense of scale, Mercury, which is the closest planet to the Sun, takes about 90 days to complete a full orbit. And the planet that we looked at, WASP 43, takes, I think, 19.5 hours. Is that right, Kevin?
That's right.
Okay, great. Well, I want to get to that. I want to cover that in more detail, just a little bit more. But Laura, since I've got you here, let's. So you're a grad student. You work with Kevin, presumably. One of the things I love about people up and coming in astronomy is learning about how they got into it. Are you specializing in exoplanet research too, or are you looking?
I am. Yeah, the main focus of my PhD is trying to characterize the atmospheres of these planets.
Great. So you're also interested in atmospheres, just like Kevin. No coincidence, I think. So, well, okay. Well, So atmospheres around exoplanets. I want to talk about how you detect that in a minute. But first, is there any sense of how the ratio of how many of all the exoplanets out there, how many have atmospheres? Do you have any sense of that yet? Is that coming out of the observations?
That's a great question. It's something that we're trying to understand right now. Actually, we're trying to figure out where the boundary is between planets that are big balls of gas, basically, like Saturn and Jupiter, and as you shrink them, they get more rocky, closer to the Earth, and we want to know how big planets have to be in order to have a big puffy atmosphere made out of hydrogen and helium, and whether they can hold on to that, and whether some of the rockier planets have atmospheres themselves. And I would say, Kevin, most planets have atmospheres, right?
Absolutely. I mean, even something like Mars, which has a very tenuous atmosphere, it still has an atmosphere, but it's not certainly anything that's thick enough to breathe on if it had oxygen, for example. But there are very small planets that we expect to be very close to their stars that may not have atmospheres simply because they're too hot.
Okay, so you're finding. So when you say most, what are we talking about? 90%, 99%? Well, just more than 50. More than 50. That's a lot. I mean, not only are there a lot of exoplanets, but that most of them have atmospheres. To me, is very exciting. Now, that's obviously there's a wide range of atmospheres, and we'll talk about some of those here in just a minute. But at least for life elsewhere, having an atmosphere is probably a good thing. So it's good to know that most planets have one. So how do you find out? What's the way when you look at these exoplanets? I mean, the fact that you're looking at them at all is amazing, but how do you find the atmosphere? How do you measure that it has one?
There's two different ways that we can measure an atmosphere, and it's a trick that we use for transiting planets. What happens is if the alignment of the planet as it orbits its star is just the right inclination, we can actually see the planet as it crosses in front of the star. This is called the transit. And also when the planet goes in behind the star, we call that an eclipse. And there's different ways of combining this information to understand the atmosphere. So, for example, if the planet is really hot, we can actually measure its emission. The planet has a lot of heat being bombarded from its star onto its atmosphere, and then it re-radiates that. And we can see that as the planet goes in behind the star, basically the difference of the planet and the star, and minus the star itself when the planet disappears, that can really tell us about the heat coming off of the atmosphere itself. In the transit, it's a little bit different. We actually measure the light coming off of the star. It grazes the atmosphere of the planet and tells us information about the atmosphere that way. So there's two different techniques that we can apply for transiting planets just to learn about the atmosphere.
So yeah, we've talked about in our other exoplanet hangouts in the past. There's two methods of finding an exoplanet at all. One is the transit method that Kevin just mentioned. The other one is another method called radial velocity, and I think there's a third as well. But they use the spectrograph and look at the wobble of the star as it goes across or goes around as a planet orbits around the star, and that's called radial velocity. And you can learn about that in any of our other hangouts. I don't really want to go into it too much here, but those are the two main ways. So you can get an idea of the temperature of the atmosphere, Kevin. But is there anything else you can learn about it? How do you find out other things about that atmosphere?
Well, there's certainly what you want to do is probe the atmosphere at different wavelengths. So when you look at the atmosphere at a specific wavelength, basically you'll be probing a particular altitude or depth of that planet within the atmosphere. And then if you go to a second wavelength, you probe a different altitude or depth of that atmosphere. So by looking at a broad set of wavelengths, you can go from optical to near infrared, you can actually probe different layers of the atmosphere and measure its temperature at those different layers, and you can really put it all together to form a better understanding, a map, if you will, of the planet's thermal structure and its composition.
Right, yeah, that second point is important. You can learn what the atmosphere is made out of, what gases are in it. And
by just looking at it in different wavelengths, different filters, and measuring the heat that comes out?
Because what happens is when, this is for transiting planets, when the light from the star is passing through the planet's atmosphere, some of it gets absorbed by molecules that are there.
Yes.
And that's something we can measure in a lab, is how different molecules absorb light. And so by comparing what we see to our data from labs, we can back out of that what molecules are in the atmosphere doing the absorption. And so we've used this technique to discover water in the atmospheres of a bunch of planets so far.
So let me make sure I'm getting this right. There's two kinds of measurements here. One of them uses a transit to measure the heat in different wavelengths coming off of the atmosphere to get an idea of what the characteristics are based on wavelength. And then there's the light passing through the atmosphere, through a spectrograph, onto and we're spinning up and seeing the spectrum, and the absorption lines that you see in that spectrum tell you some of the elements that might be in that atmosphere. So, for example, if it has water vapor, there would be an absorption line at the water vapor line.
Right.
Okay, so good. Okay, so let's move on to the WASP. What is it? 43b. I keep for some reason it's just not sticking in my head. And so you started on this a little bit, Laura. So I'll let you go ahead and finish. Tell us a little bit about this planet. How far away is it?
Wait. I want to know why it's called WASP.
Oh, okay, Carol.
That's a good question. It was discovered by a ground-based planet search using the transit technique to look for periodic dips in brightness of the star caused by the planet transiting in front. And I think the acronym stands for Wide Angle Search for Planets or something. It's a British planet search program. And 43 is because it's the 43rd one.
So they get to name it, basically.
Yeah.
It's like Kepler gets the name there, as WASP gets the name there.
Yeah, which I suppose is only fair because they.
Thank you.
Well, it's only fair, but they need to come up with better names. I mean,
It's okay. We've got WASP. There's another survey called HAT. We've got the Kepler.
Yeah.
I don't know. I keep telling my mom I'm going to name a planet after her. She doesn't really know that I'm not searching for things. I know that I can't name them after her, but I keep saying it.
Yeah, you don't get that privilege, I guess. None of us do. Okay.
Can you hear me?
Sorry, we just got a freeze.
Yep.
Yeah, we had this problem last week.
Okay.
Are we back?
Yes.
Yeah, I think so. I think we're back.
We're back.
Okay.
Okay.
So what I was saying was WASP 43b is about 300 light years away from us, which sounds like it's pretty far, but in the scale of the universe, that's actually incredibly close. The Milky Way is 100,000 light years across. Kevin, is that right? 100,000 light years?
Give or take.
And so this planet is just 300 light years distant from us, and that makes it easier to study because it's orbiting a star that's relatively bright. It is twice the mass of Jupiter, so Jupiter is the most massive planet in our own solar system, and this planet is 2 times more massive than that. And the other thing about it that makes it really different from what we know of from our solar system is just how close it orbits to its host star. So it takes less than 20 hours to complete a full orbital revolution around the star. And that means that it's really roasting hot because it's so close to this really bright star. So yeah, that's it in a nutshell. And it's representative of a class of planets called hot Jupiters, which are so named because they're extremely hot, orbiting very close to their host stars. And these were among the first planets to be discovered. They transit frequently, and they make a big tug on their host star, and so it's easy to detect them both with radial velocities and transits. And so although they're relatively rare in terms of what kinds of planets orbit are most common in the galaxy, they're among the easiest to study.
Yeah, that's an interesting point. It turns out I think Neptune-sized planets, right, are the most common. Is that what I heard? Of all the
and smaller.
Yeah, those are much more common. So we have a 2 Jupiter mass planet. You've also said that its orbit is really fast. You said it just goes around in about 19 hours, right? That thing is really spinning.
Yeah.
What does that mean? It's tidally locked around the star. Is one side always facing it?
Yes. Yeah. So just like the moon has one side always facing the Earth.
Okay, so here Scott's showing us the actual map that you guys made. Why don't you, Kevin, you want to tell us about what we're looking at here?
Certainly. So this is a artist's rendition of the type of measurement that we made, and it's actually showing the heat of the planet as it goes around the star. So we have the star in the center of WASP 43, and we're showing the planet at different phases. So what we did is we actually observed the planet for 3 complete rotations. So it went around its star 3 times. And because it's tidally locked, the bright side of the planet, the day side of the planet, is consistently the day side of the planet and is bombarded by all of this heat from its star. So the day side is very, very hot, and that's shown in white on the graphic. And as the day side, you see at 0 degrees, which it's a full-on day side that we can see. As the planet orbits around its star, we begin to see, phases of the moon. We begin to see that the night side come into view, and we can see that it is very cold on the night side, less than 1,000 degrees Fahrenheit, and that's depicted in black there. And so when at 180 degrees, it's the full-on night side, we don't get a lot of signal from the planet itself. And then as it comes back through 90 degrees and 0 again, or 270 and 0, then the day side comes back in, and we see it's essentially a sinusoidal increase in emission from the planet, and then a decrease, and then increase and decrease.
Okay, I want to get to a couple of relevant comments or questions on the Q&A app. Eric Charland is asking, how precise are those measurements of gas in exoplanet atmospheres? How precise are they? In other words, how well do you know these temperatures?
Laura, do you want to talk about how well we've constrained the water on this planet?
Yeah, I can talk about that. So like I was saying earlier, one of the things that you can learn about the atmosphere is what it's made out of. And so for WASP 43b, we made the most precise estimate of the water abundance, so how much water is in the atmosphere for any exoplanet so far. And we measured it to within about a factor of 10 or so. When we talk about water abundances, we often compare them to the expected amount of water you would get in a gas with what's known as solar composition. So if you took the material that made up the sun, there's some oxygen atoms in there, and you cooled it down to the temperature of the planet, it would form water. And so what we measured for WASP 43b is that its water abundance is about between 1/2 and 3.5 times the expectation for this solar composition gas. And so a factor of 10 is really stunning to achieve for something that's 300 meters away.
Yeah.
And not only is it precise, but it's also something we can't measure for the solar system planets at all. So Jupiter and Saturn are so cold that their water has frozen out in deeper parts of their atmospheres, and it's out of reach for us to study. And so these hot Jupiters have such high atmospheric temperatures that water is all in the gas phase. And we can use them to try to learn about how much water went into forming them. And water is thought to be a really important building block for planet formation. That's one of the reasons we're so interested in this.
What about the temperatures themselves, the temperature measurements themselves? How accurate are they?
Kevin?
The temperature estimate has to make certain assumptions. The difficulty with the measurement that we're making is we're really looking at the planet's entire face when we're making a measurement. So the day side, for example, we can't pinpoint or make a temperature measurement at specific spots on the planet's surface, we kind of have to take everything as a whole. So the measurements are very precise when you average over the face of the planet itself that we can see. But it's difficult to actually say, well, this exact spot within the planet has this particular temperature, because of course there's going to be more local variations in the temperature, just like what we have here on Earth. It's not going to be the same temperature everywhere in North America. It's going to vary. But if you take an average measurement over the entire continent, we can say with fairly good precision what that average temperature is.
Yeah, so it's within about a couple hundred degrees or so.
A couple hundred degrees, okay. Well, Scott's got an animation up. Who wants to talk about that? How about you? Go ahead, Laura.
Oh, this is Kevin's baby. I'll let Kevin talk about it.
Oh, okay, Kevin then, sorry.
All right, that's fine. So what this graphic is showing is I'll start in the top left-hand corner. It is the emission spectrum, the amount of light that we're measuring as a function of wavelength as the planet makes one complete rotation. So the time-lapse video shows what's called the spectrum, and there's a water absorption feature. So between 1.3 and 1.6 microns, roughly, there is, in white on the graphic there's a large water absorption feature. And we see that water because the amount of light that we measure dips there. So at certain phases, there's a dip around that region, and we can say, well, that is because we measure water inside the atmosphere. And the reason why this entire red line is going up and down is, as I mentioned before, the planet's day side comes in and out of view. So as the day side comes into view, you can see that on the bottom with these brightness temperature maps, the brightness increases. And then as the night side comes into view, the brightness decreases. And that's also reflected with thermal profiles. So we have a measurement of what the temperature of this planet is over this face. On the day side, and notice it's quite warm. It's in the 1500 to 2000 Kelvin range, which is up to 3000 Fahrenheit. And then as the night side comes into view, the temperature essentially drops like a rock to something below 1000 Fahrenheit.
Oh, that would make sense.
And again, on the bottom, these temperature maps, there's just 3 different examples of what the temperature is at different altitudes. So wavelengths, different wavelengths provide different depths inside the atmosphere. So you can see some are brighter and some are cooler.
So I have a question. So you have very hot atmosphere on one side and cooler on the other. One would expect there would be like really amazing winds on this planet, but apparently they're insufficient to actually circulate the atmosphere enough to equalize its temperature because it's so close to its parent star. Is that the idea?
So there are very strong supersonic winds on this planet, and the question is it's a question of time scales. How long does it take to push the wind from the day side to the night side,
right,
versus how long does it take for that heat to re-radiate out? And as it happens with this planet, it doesn't take long for the heat to basically re-radiate. So the wind, although fast, just doesn't have enough time to push that heat from the day side to the night side.
So what obviously you've used the Hubble to make these measurements, and we're looking at the wavelength go up and down in the near IR around the 1.3 to 1.6 wavelength range. What instruments were used to make these observations on Hubble?
With Hubble, we used a Wide Field Camera 3. That is
the old standby.
Yeah, the old standby, the old dependable, right? It's came into commissioning around 2009, I believe. And it's just been a fantastic workhorse for exoplanet characterization. It's an amazingly precise instrument. It has great stability, and it allows us to make high precision measurements of exoplanets, particularly if you're interested in water, because it has that sensitivity from 1.1 to 1.7 microns, for example, in the case that the measurements that we used here. So it's been a really great instrument to use, and we're going to be testing it further, actually, with other wavelengths and other planets, of course.
Oh, that's what I was going to ask you next. So there are other planets in your future then that you're going to be trying to do these maps with, right?
Oh yeah.
Do you have Hubble time coming up this year, or is it down the road a bit?
We have observations that are still going in this year's cycle.
Okay.
And we're asking for more time.
So, is this a difficult thing to do with Hubble? Is this a hard measurement to make? And by hard, I mean
Yes.
the exacting and difficult to process the data and understand what you're looking at.
To do these observations, like Kevin got into this a little bit about how fantastic their C3 is, but these instruments were never designed to do the kind of stuff that we do. We're measuring the brightness of the star at precision on the order of, less than 100 parts per million. We're measuring very, 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 very tiny changes in the brightness of the star. And the instrument has time-varying sensitivity, and so that basically they're instrument systematics that are 2 orders of magnitude larger than the signal that we're trying to detect. And so there's a lot of data processing that goes into seeing what we see.
Yeah, that's what we built Kepler for, was to make that kind of precision measurement. So I can see. So I see what you mean about it not being designed for that, but you're still able to extract this information. That's
yeah, and it comes out looking fantastic. This is the first instrument where we've had spectroscopy that really matches up with models for what the atmosphere should look like. So we're really believing this data. We're observing in a new mode that was developed specifically to observe bright targets, like what we're doing.
A new mode? Can you describe what do you mean by that?
Yeah, so this is a really cool thing. So the detector will saturate pretty quickly for the very brightest targets, and it takes some time to read it out. And so every time you take a short exposure and you waste a bunch of time reading it out, you are losing time on target, like on sky, when you're actually detecting photons. And to help get around this, the folks at Space Telescope designed a technique that allows the telescope to sort of move the target star on the detector over the course of an exposure, and that smears out the light, and so you don't get saturation as quickly. And so that allows us to take longer exposures and use the telescope more efficiently for these really bright targets. And that totally broke open the door to doing observations like this.
Oh, that's wonderful. We should have a hangout on that technique, Carol. I want to learn more about that.
Yeah. So the idea is, if you have to take a very fast exposure and then read it out, you're spending all your time reading the detector.
Right, exactly. So
whereas if you have a technique to increase the exposure time, then the readout time is less % of the entire cycle.
Right, exactly. So what we effectively did is increase the amount of exposure time we can get by a factor of more than 5.
Wow.
From like 10% efficient to 70 or 80% efficient.
Wow, that's great.
Yeah, that is amazing.
Yeah.
So can ground-based telescopes do this, or is this something that we got to be in space for?
This is something we have to absolutely be in space for. So the measurement that we made, remember the planet orbits in 19.5 hours. So it's essentially impossible to stay on a target for that long a time from the ground, because obviously you have to deal with things like the sun coming up. So first of all, you need a space telescope for that because of the duration of the measurement, and also because of the precision. We are measuring water in this case, and it can be very difficult to do that when you're on the ground, because you have a pesky thing known as Earth's atmosphere that's in the way and absorbing water.
Keeping us alive.
Well, it's great for that, but it's really annoying for astronomers.
It is.
Yeah. Okay. Well, that's great. So Atom Synergy has a question on the Q&A app that I've been reading, and I don't understand one of the terms he's using, but I'll read it to you. So he's asking, as I understand it, both the hot spot on the day side and the cold spot on the night side of WASP 43b were observed to be offset relative to the substellar and anti-substellar points where they might expect it to be. What are the likely reasons for this? I don't know what a substellar point is.
That sounds like a scientist asking that question.
That is a well-posed question, actually.
Yeah. Adam's always got good questions.
Okay, so the substellar point is the point that is closest to the star, point on the planet that's closest to the star. So you would expect that point to be the hottest. The anti-stellar point is the opposite. It is the point on the planet that is furthest from the star. This is going to be the night side, so you'd expect that to be the coolest. I think we do have a graphic that shows the white light phase curve. If we can bring that up. And that really shows, okay, perfect. So this is a graphic here, and it's showing as a function of orbital phase. So as the planet makes one complete rotation, there's an increase in brightness as the day side comes into view, and right around 0.5 we see this drop. That right there is the secondary eclipse, where the planet goes behind the star. And then again, as the day side goes out of view, the temperature drops. What you'll notice is, okay, if there were no winds, what you would expect is the brightness to peak somewhere around the secondary eclipse, about 0.5, and then you would expect to have a minimum around 0, orbital phase of 0. And that's not happening in this case. So you can see the minimum probably occurs closer to a phase of 0.1, and the maximum occurs closer to a phase of 0.4. So the maximum, we can explain that by winds. So what happens is that the circulation pattern on the planet pushes that hot day side downstream a little bit, and then by the time it re-radiates, the planet has already rotated a little bit, and it's peaking around a phase of 0.4 to 0.43 roughly. The night side, that is an excellent question, and we can explain that. None of the models that we have right now adequately explain why the night side has been shifted to later on past transit. So that is an open question that we're still looking into.
Nice, and well done, Adam. Thank you for that question. Craig Landon is asking, also on the Q&A app, given that there are as many types of exoplanets as there are types of stellar classification, is there any exoplanet classification based on composition, atmosphere, size, anything except these names based on solar system types? Is there any classifications based on what the planet itself is like? It's the way I read that.
There are a couple of ideas that scientists have put forth based on composition and temperature that we believe might classify a planet. One example, for example, is a thermal inversion. So all of the temperatures that we've shown decrease with increasing altitude, and it is fairly, basically, as you go higher up, it gets colder. And some measurements have suggested that planets might get hotter as you increase your altitude. And there is actually a debate going on about whether or not that's true. But people have predicted that there are two different types of planets, two classes, based on whether you have a temperature inversion or do not. Another way of classifying a planet is how much carbon there is versus how much oxygen. So there's an interesting debate also about, we call it a carbon to oxygen ratio. If there is a lot of carbon on a planet, you might have interesting chemistry going on in its atmosphere, versus if you have more oxygen in the planet, you'll have different chemistry going on. So that's just two ideas of what people have that they can hopefully use to classify planets. But certainly this is an ongoing debate, and it will be for some time until we have a lot more measurement of these planets that we've characterized not just a dozen or two, but maybe 100. Then we'll really be able to pull out statistical information about these planets.
So I have a question then. You're talking about using inversion as a classification, but as we know, the Earth has inversion layers too, but they're not persistent. So it seems like maybe some other planets might not have persistent inversion layers.
No, that's not true, Carol.
Oh, okay, sorry. Never mind. Excuse me, I should go back to reading a book.
We're taking baby steps here, right?
Yeah.
So something means that we've measured a thermal inversion in an exoplanet atmosphere, and then they came back later and said, oh, now we don't see it.
Yeah.
My much on something being wrong with the instrument or the data analysis, rather than the planet actually changing.
Maybe the planet changed. You know I'm going to jump in the fray, Tony.
I love it. Thank you. Okay, so Michael Jobin is back giving us some comments. Hi, Mike. It's good to see you again. He's commenting that it's amazing that you know it is tidally locked. That's true. I mean, it is. What are the characteristics of a tidally locked? I mean, let's say it weren't tidally locked. What would you be able to tell from the thermal maps that you're making that it's not, or is that something that's relatively easy to find out?
Yes. So there are planets, for example, that have large eccentricities. So that means that its orbit isn't circular around its star. If it has this highly eccentric orbit, what happens is the day side isn't a permanent day side, and the heat signature that we're seeing, the increase and decrease in flux, is not it's not timed, synchronized with the orbit of the planet, and so you get an interesting ratio where perhaps the planet rotates 3 times for every twice it goes around its star. And it's an interesting play on the dynamics and the circulation of those planets. In this case, we do know that the eccentricity is very much near 0, and so it is tidally locked.
Nice, good job. Thanks, Michael. And he's also commenting. He commented that I like atmospheres. I use one every day. Yes, I do too. So, and one more comment here from Cecil Morgan. Let me get this.
That's a really good question there.
Yeah, +3 on this one, getting voted up. WASP 43b was described as being gravitationally locked to its star like the Moon is to Earth. Would be more accurate to say there is a permanent density and temperature gradient towards the star. That is not necessarily the same as the planet's spin rate.
Yeah, because the planet doesn't actually have a surface.
Right, it's a gas giant.
Such thing as a face. Yeah, so that is a more accurate way to describe what we're talking about.
Good, nicely done. So, how long did it take to get this map built? In terms of observation orbits or whatever, how long was it? Was it a long process, or was it?
Well, it depends on who you're asking. Like, in the scheme of things, it wasn't that much time in total. Kevin, how many orbits have you used? 51?
61 orbits.
1 orbit, and each orbit is 96 minutes long. So you can
Whoa, that's a lot.
Yeah, so that's quite a bit of time.
Yeah. So it was a really intensive observational program. This is, I think, the most Hubble time that has ever been devoted to a single exoplanet, ever.
Wow.
But at the same time, you know, when I told my friends, oh, Hubble's looking at our planet right now, and then the next day it was practically done, that made it seem really quick. I was enjoying my moment in the sunshine when that was going on. But so as far as telescope allocation time goes, this is a lot.
Yeah, that's a lot. That was a lot, yeah. So Eric Charlin on the Q&A app is asking, are you guys on Twitter? Can you be followed?
I have a Twitter account.
Can you be stalked?
I posted one thing on it.
See, we can change that.
Yeah.
Fun.
I too have a Twitter account, but I don't tweet on it. I just follow.
Yeah, my Twitter handle is like Laura Kreidberg. I can put it on my little name tag.
Well, if you don't tweet on it, there's no point. You guys start tweeting. Let us know what you're doing.
I was thinking it would be really fun to tweet an observing run sometime, to go through the whole process of like flying down to Chile or whatever it is, and like all of the touch and go at the start of the night when we're trying to get our target aligned and stuff. I think people might think that was cool if I could do that on my Twitter account.
Oh, that's really great. So let's talk about the future a little bit. You're gonna apply this technique, the measuring these thermal maps, to other stars. How are you going to pick which stars to look at?
This is actually it's an interesting question. This method that we used is really restricted to planets with very, very short orbital periods, basically less than a day. And so we have really just a small handful, 4 or 5 planets, hot Jupiter planets with orbital periods less than a day that we can apply this technique to. Outside of that, it becomes much more challenging for more technical reasons for the telescope itself than the observations. What happens with the telescope, for example, is they have to go through recalibrations every 14 or so orbits, which requires you to actually stop making measurements. Additionally, what happens with the Hubble Space Telescope is that it orbits the Earth, and most you're going to get about 7 HST orbits of the Earth before it crosses what's known as the South Atlantic Anomaly, and that is essentially a region, high ionized region in the South Atlantic where you have to shut down all the instruments. So it becomes really difficult to make this type of measurement over a span of 2 or 3 days because you have all of these different physical effects that you have to deal with that interrupt your measurements.
Okay, so
I should add though that this is going to change big time when the James Webb Space Telescope is launched.
in what way?
Because that will be so a whole bunch of ways. First thing is that it won't be orbiting the Earth. It'll be in a heliocentric orbit, so orbiting the Sun. And that will allow continuous observation of any target you want for a much longer time span before you get into these obstacles like Kevin was talking about. And it's a much bigger telescope, and so we'll be able to observe fainter target stars, and so that really increases the sample size of planets that we can look at.
But are you still restricted to those planets that are less than a day?
No.
Okay.
So because we can observe for longer than a day.
Oh,
Yeah,
okay.
so for longer period planets, we can observe smaller planets, fainter target stars, and we'll also get wavelength coverage that is much greater than what Hubble offers, and so that'll allow us to look at different molecules and at cooler temperature planets and all kinds of stuff. So we're really looking forward to that.
Yeah, so that's everybody's waiting for JWST. Nice time to have that up there and have Hubble up at the same time. Patrick Calhoun on the Q&A app is going, how long till we send a probe to an exoplanet? I can answer that one. Long time.
Yeah.
A long time. Although I think, Scott, you're building one in your basement, right?
Oh, I live in an apartment building in the city of Los Angeles, so yes.
That would be your neighbor then.
Yeah. Because Patrick did ask this on Twitter as well, and I think it's something that we have to consider, the fact that we have to propel something to another star system and somehow deal with telemetry on that. We would have to have something extremely sophisticated, and it would take thousands of years to be able to get anywhere near being able to do something like that.
Right, so we're looking at 260 light years away, and even if we went at the speed of light, it would take 260 years to get there, and then we have all kind of other issues. So it'll be a while.
Yeah.
Unless somebody can discover a way around all of those
There was actually
physics laws.
some chatter about sending a probe to Alpha Centauri, where an Earth-sized planet was recently discovered to be orbiting one of the stars, and I think the idea was that it would cost like $1 trillion and use technology that hasn't been developed yet, and so that's the closest star system to us.
Right.
Okay,
And it would be powered by space unicorns.
That's a good power source, by the way. Those are really powerful. Let me.
I just want to. Okay, sorry, you guys. Just to back up something that Kevin said. This is actually.
I thought you could bring up a space unicorn. Go,
No,
Carol, go.
I don't know if you the Exoplanet app, and on this side, which you can't. So I'm advertising. Go get the Exoplanet app. I don't expect you to be able to see this, but
We're seeing it. It looks pretty good.
Okay, so there's the mass and the orbital period, and notice there's hardly any less than a day over here. So those are the ones that Kevin and Laura are looking at. They're down there. It's just a handful. And some of them are small, so they're going to be really faint. Anyway, that's the
Nice. Good job. That's awesome, Carol. Thanks. So yeah, download the Exoplanet app. That's a.
And you can do your own correlation diagrams and look at the orbital systems and all that stuff.
So Laura, we have a few
on iOS or Android, or how? What is that?
Mine was on an iPhone, but I think, and he has a website too. So he has a website that has all the data on it too.
Because we can tell people to do that, but we need to tell them where to go to get it.
Okay, I'll find it.
Okay.
Thank you, Carol. I love you.
Yeah. All right, you two. So Laura, while we have a few minutes, I'd like to ask you. I know you're a grad student. You're studying to get your PhD now. What advice? First, I'd like to know two things. What made you decide to get into astronomy in this particular career path? And do you have any advice for other, maybe girls in high school thinking about doing something similar? Tell us your story a little bit.
Yeah, so I was fortunate to have a lot of support for my interest in science when I was in high school, and when I got to college, I realized that all of the classes that I wanted to take were astronomy classes, and so I went for it. and I think this stuff is so cool. I decided to keep doing it. But yeah, for young women in school who are thinking about science, like, go for it. It's so fun. I mean, it's like I'm having a blast. And
Did you ever have telescopes growing up or anything like that, or it was just all your courses?
No, yeah, just in school.
Oh, good. Well, all right. Well, thanks. Yeah, I wish you luck. And when do you defend your thesis?
Probably in spring of 2016. So I have about a year and a half left.
Okay, that's always an open question, I know, but I didn't.
Yeah.
Okay, Scott, am I missing anything? I think I got them all. Am I missing
I think we got them all as well.
Okay.
You were on it today. And Carol did just share with me, so I'll do a quick screen share as well for that app that she was talking about. Is available for iPhone. You can go to exoplanetapp.com to take a look at it where we're going through. So
there does seem to be one on the for the Android. I do know that the gentleman in Europe who does the Exoplanet app, the Exoplanet database, the iPhone, iPad app is the one that he populates. I haven't tried the Android one. But also in the app, he also has a reference to his web page. But he's like a graduate student. Okay, so no complaining about why it isn't on multi-platforms. He, like Laura, is supposed to be doing his thesis.
Awesome.
In fact, I think he actually got his degree and he's now gainfully employed somewhere. But he did this as a part of, when he was researching exoplanets. So don't hit him too hard about it.
I was just curious. I want it on my tablet. I'll have to look.
Yeah, I'm going to look and see if I can get it on Android as well. Thanks for sharing that, Carol. That's really cool. Okay, well, I guess that's it for this week, guys. I hope you'll tune in next Thursday where we will have the Hubble Hangout on the nuts and bolts of Hubble. I mean, have you ever wondered how to drive the Hubble Space Telescope? How do you work it? How do they point it? What are they? What are the mechanics of actually operating the Hubble Space Telescope? We're going to have engineers from Goddard with us next week to talk more about that. Also, don't forget about the Intrepid Museum exhibit going on right now and the talk going on next Wednesday. So if you're in New York, we hope you can stop by and check that out. Carol, Scott, anything we should add? You want to add anything?
No, it's going to be awesome. I can't wait to meet up with the engineers at Goddard.
I know. I've always wanted to learn how to do that. Laura and Kevin, you guys were awesome. Thank you for this. Really interesting work. Thanks for all the great information and sharing what you've been doing with us. And I guess we'll close it we'll close it for this week, space fans.
Space fans.
Thank you for watching, and as always, keep looking up.
Thank you.
Bye, everyone.
Bye. Bye.
A brief overview of the work you've done, a brief summary of the work you've done, and then I want to go into exoplanets in general just a little bit.
A lot of the work that I've done focuses on extrasolar planets, particularly the characterization. So what I try to do is try to understand what the atmospheres of these exoplanets are made out of. We know typically they're fairly large, gas balls, and they can have hydrogen, helium, but we're more in the other aspects, water, carbon monoxide, carbon dioxide, methane, that sort of thing. And to understand really the circulation, the temperature, everything about these planets that can tell us a little bit more about our own solar system and the galaxy as a whole. So I really try to understand exoplanets and where they come from based off of our measurements with, for example, Hubble Space Telescope.
Oh, great. So let's talk about that a little bit. So what are you finding out about the characteristics of exoplanets? I mean, this is, and check that out. It sounds like a lot of fun. So with that, I'll go ahead and get started. The thermal map of WASP 43b. That's the topic of today, and to joining me to help with the discussion is Dr. Carol Christian, as she is always with me every week. She's the outreach scientist for the Hubble Space Telescope. Hi, Carol. Also,
hello.
Also with me is Scott Lewis, who is the driver of the internet for us. He monitors all the social media streams and posts images and comments and keeps things going while we're online having the discussion. Hi, Scott. Welcome.
Thank you, Tony. How's it going?
Oh, really good. So why don't you do this week? Tell people how they can interact with us on social media.
a multitude of ways that you can interact with us. Since we're streaming live on YouTube, you can make comments directly onto YouTube, but we also have the Q&A app enabled. So on the bottom left-hand side of the window, you should see a little yellow prompt.
This is a brand new field of study, relatively speaking. Exoplanets are just everywhere now, it seems. So what are you finding out about them?
Well, there's certainly tons of surprises everywhere we look. We've made measurements over the last 10 years, and it seems that every time we make a prediction, something comes up and we see something completely differently. It's not that the predictions aren't accurate, it's just that the universe is so much more diverse than we expect. So sometimes we might hope to detect methane and we don't, and sometimes we might expect to, we don't expect to see it, and we do. For example, with the observations that we're doing here, we would expect maybe that the planet might be similar in temperature on the day and the night side, and this was in fact surprising when we saw that the day side was so much hotter than the night side. So it just goes to tell you that they're really...
They'll actually open up a window and allow you to ask us questions directly. We can select them. That's available on YouTube and at Google+. And we're also over on Twitter using the hashtag Hubble Hangout. And I will be tweeting throughout this entire time, so I would love to tweet back at you. And also the event page, where I will be posting some images as well. So many ways for you to be in touch with us, and we love getting your questions and comments and answering them on air.
Okay, that's with all things when you're talking, Scott. I phased out there. Did you say the Hubble Hangout hashtag part 2?
No, I don't ever. Yeah.
Yeah, okay. Okay, good. I was reading what you were talking. All right. So today we have with us Dr. Kevin Stevenson. He's a NASA Sagan Fellow at the University of Chicago. And we also have Laura Kreidberg. She's a grad student at the University of Chicago, here to tell us about their research where they looked at an exoplanet. And why don't, Kevin, I'll start with you. Why don't you give us a... Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and I think we have a really great hangout planned for you, although I say that every week because we always have great hangouts planned. I think you're going to enjoy this one, though. Astronomers using the Hubble Space Telescope have pointed it at WASP 43b, an exoplanet that we'll be talking about later on, and made a thermal map of it. We'll also talk about what that is. So before I get started with this, I want to mention real quickly that if you're going to be in New York, I want to remind you that they have the Hubble at 25 exhibit going on there. And I also want to note that they have a next Wednesday, they're going to be having a public event where they'll have astronauts who's worked on the Hubble Space Telescope giving some remarks. So if you're in New York, I would highly encourage you go.